Hi there, welcome back to the chemistry channel. Last time we've discussed about reaction kinetics and order of a reaction. And I said that the speed of reaction is given by this differential term here, and it's equal to a constant times the concentration, the initial concentration of reactants to the power of their stoichiometric coefficients. And we also said that the order of reaction is the sum of the stoichiometric coefficients for a more general, in the most general form there is. I also gave some example of a first order reaction where we said that the decomposition of nitric pentoxide, it's a first order reaction because we don't need the collision between two molecules for this to decompose. One molecule is sufficient, so we have a first order reaction. We also gave example of a fractional order of reaction where n was 1.5 instead of what theoretically predicted, the sum of the stoichiometric coefficients being 2. And the reason for that is that the reaction undergoes a more complicated mechanism in several steps. So therefore the speed limiting step will determine the order of reaction in essence. And we also took even more complicated reaction forms where we said that in this case you have to be suspicious if the order of reaction is way bigger than 3. Even the reaction of a third order, that means you need 3 molecules, the collision of 3 molecules for the reaction to occur, and they are very, very seldom. That means the probability for this reaction to happen, it's very extremely low. So therefore one has to be careful about this. So what we determined theoretically turns out that in practice is completely different, and usually the order of reaction is given by the step that is the slowest. That's also referred to as limiting step, reaction step. In order to understand better how you can determine the equation for the speed of reaction from the case where you have the reaction occurring through multiple steps, so it has a more complicated mechanism than is given through its simplest form. It will help if we take several numerical examples that we are going to solve next. So the first numerical example that we are going to take is the decomposition of ozone into oxygen. You can see here that from its simplest form, 2 ozone molecules will react and lead to 3 oxygen molecules. So normally, theoretically, we would write that the speed of reaction is a reaction constant times ozone to the second, the stoichiometric coefficient. However, I can write this reaction in a different way. I could also write it as ozone going to, for example, 1 oxygen molecules plus 1 oxygen radical, in which case the speed of reaction would be K ozone to the stoichiometric coefficient. Obviously now the order of reaction in the first case would be 2, in the second case would be 1. However, experimentally it has been determined that this reaction proceeds, the mechanism of reaction proceeds in several steps, which is the first step would be 1 molecule of ozone decomposes into a oxygen molecule plus a oxygen radical, which we also can write it as like this. It has been experimentally shown that this is rapid. So this equilibrium is attained rapidly, and it's followed by a second reaction step. So this oxygen radical reacts with an ozone molecule to produce two oxygen molecule, and this is slow. Obviously, if we add these two equations, we will get to ozone, that is twice, leads to the formation of what we had in the beginning of 3 oxygen molecules. So let's determine now what is the speed of reaction given the reaction mechanism. Now, obviously, the speed limiting step would be the second part, the second equation, the slow reaction step. Now, if we are going to write the speed of reaction for the slow reaction step, we would have the velocity of the reaction times the reaction constant. Obviously, this one is different from this one, so we'll refer only to the second equation, times the initial concentration of the oxygen radical to the ozone, and it will look like that. Now, the concentration of the oxygen radical can only be calculated here by how fast it's been produced in the first rapid equilibrium reaction. So in order to calculate this, we are going to calculate it from the equilibrium constant of this reaction. Because this is rapid, then we know that K, for example, the equilibrium constant for this reaction, is the product of the product concentration divided by the reactant concentration. So from here I can pull out the value of the concentration of the radical as being K times O3 divided by O2. Now, if I plug in the concentration for ozone and the speed of reaction, I will have a K times equilibrium constant times O3 ozone to the square divided by O2. I'm sorry you didn't see that. Now you can see it. So it will be the reaction constant times the equilibrium constant times ozone concentration divided by O2. But because this is a constant, the equilibrium constant is a constant, then we can say that the speed of reaction is K prime times ozone squared divided by O2. So now we have obtained a kinetic law that is completely different from what we would have obtained here theoretically from the simple reaction equation. In practice, this is totally different. So once I know the mechanism of the reaction, I also know the kinetic law that it abides by. Thanks for watching. We'll meet next time with another numerical example. And until then, bye-bye.